I'm very glad to have this talk today. So, as Scott said, I'm Eleonora Grassucci, a PhD student at Sapienza University of Rome, and in particular from the ISPAM lab, which is Intelligent Signal Processing and Multimedia Laboratory. And so basically, let's start. So we'll talk about complex and quaternion numbers. Then we'll see a practical uses of such theoretical stuff in nowadays deep learning applications. Then we will go beyond quaternion numbers, and we will extend this approach to hypercomplex neural networks. We'll see some experiments on image and audio processing, and then we will conclude. So first of all, what are we talking about? Quaternions, I like to say that have more applications than we expected, since they can be involved in natural image processing, avionics, robotics, audio processing, graphs. Basically, if we have multi-dimensional inputs whose dimensions are highly correlated, or we are in a 3D space and we have to rotate and translate objects in a 3D space, then quaternions are a good choice. Basically, complex quaternion numbers and more in general hypercomplex numbers rely in the middle of real Clifford algebras and Cayley-Dickson algebras. A bunch of history, quaternion have been discovered by Hamilton when he was working on the Broom Bridge in Ireland. And he got this flash of genius, and then a stone was posed on the bridge to remember this flash of genius. Let's go more in detail with some theory. So complex number is defined by two real value coefficient and one imaginary unit. A quaternion number instead is composed by 4 real valued coefficient and 3 imaginary units. Most important thing is that for quaternion numbers, the following properties hold, and mostly the product is non-commutative. So when multiplying two quaternions, we have to pay lots of attention on modeling the interplays among imaginary units. So Hamilton introduced the Hamilton product. So basically, suppose that we have a quaternion W with real valued coefficients W, 0, 1, 2, and 3. We want to multiply another quaternion X that have real value coefficient X, 0, 1, 2, and 3. The Hamilton product proposes to organize the real valued coefficient of the first quaternion W, that basically could be a weight matrix for neural networks, in such a way that each real value coefficient, each coefficient of the weight is multiplied by each coefficient of the input. Let's go more in detail. Basically, when we talk about, for example, fully connected layers, so standard fully connected layers in the real domain, we have W, which is a weight matrix that contains, for a weight matrix of 4 by 4, 16 different parameters. In the quaternion domain, instead, the quaternion fully connected layer will the weight matrix W to have the same dimension, so 4 by 4, but with just 4 parameters. So basically, just with this construction, we are reducing the number of parameters to 1 over 4. As well, when we talk about convolutional layers, now W is a matrix containing filters for the convolution. As well, the convolutional layer in the quaternion domain contain the filter a batch of filters as a real value coefficient in the quaternion and can be organized as following. So through this organization, quaternion layers can share basically filters and weights for each quaternion input dimension. So for example, W0 is multiplied by X0, X1, X2, and X3. And this is a great advantage for quaternion neural networks since a small change in the input is reflected also in the weights. So basically, if the dimension of the input are correlated, then we can preserve such correlations through the sharing of weights. Let's see some examples of quaternion neural networks, for example, in processing RGB images. So color images have typically 3 channels, red, green, and blue, that are processed as separate entities in real-valued convolutional neural networks. So basically, suppose that we have a pixel, and that pixel represents a purple, the color purple. The color purple is obtained by a combination of the red and green and blue channels. In real-valued networks, we lose this combination and we process each channel separately. When we process color images in the quaternion domain, we pad an initial 0 channel to match the desired dimension. So we need 4 channels. So we have to pad an additional information in such a way to reach the fourth dimension. But we process the 4 channels as a single entity. We preserve the original structure of the image. We proposed several models leveraging this representation. We propose a variational autoencoder in the quaternion domain. So we had to
Harry, could you please mute your mic?
Yes.
Please.
Okay. So, sorry for that. So if we represent the variational autoencoder, which is a common generative model in the quaternion domain, we have to rewrite the cross-entropy loss, the Kullback-Leibler divergence, to process the covariance matrix of quaternion inputs. And you can see the code is publicly available on GitHub. As well, we propose, we test a quaternion generative adversarial network on different datasets, and you can see that the quaternion valued generative adversarial network on the right outperform the real valued generative adversarial network on the left side. And I want to recall that in our experiments, the quaternion models gain better results while reducing the number of parameters. So it's quite interesting. Coming to audio, we deal with 3D audio. So basically, we take into account first-order ambisonic microphones that are composed usually of 4 microphone capsules. So the first one is an omnidirectional microphone, and the other 3 capture instead the acoustic velocity information. So what we have is that we have 4 channels highly correlated. And these perfectly fit in a quaternion, since we have seen that for quaternion applications, we need 4-dimensional inputs that have highly correlated components. So basically, we test this approach in a sound event localization and detection task, and we see that our approach with the quaternion sound event localization detection model outperform the baseline real-valued network on the tau spatial sound event ambisonic dataset. What's more, we test some scores on the computational complexity and storage memory and runtime memory and so on. And we saw that indeed our approach is faster in inference time, which is crucial maybe for online application, requires less storage and also runtime memory, but also reducing the number of parameters. So I think that it may be crucial also for embedded applications. So first recap, we've seen that Quaternion neural networks save the 75% of parameters with respect to real-valued counterparts, and can achieve better or at least comparable results leveraging the Quaternion algebra properties that allowed for exploiting correlations among multidimensional inputs. However, we have seen that Quaternion neural networks are basically limited to 4-channel inputs, since the structure of a quaternion requires 4-dimensional inputs, and sometimes we have to add a padding channel, for example, when we process RGB images. We've seen that in some cases, such that the first one, so basically in this case, the network was faster with respect to other baselines, but sometimes when we larger scale the problems, the implementation may be quite slow. So we asked, how can we preserve these pros and these advantages while extending so disadvantages basically, and the approach to every dimension, every input, so basically with every dimension. And that's why we proposed another approach that is based on the Kronecker product, so another product. The Kronecker product is basically a sort of other product, and as you can see here, we can start from two by two matrices. Basically, it's something like the 7 matrix is inserted in the first one, and then we squeeze the dimensions, unsqueeze the dimensions, so we pass from a 2 by 2 matrix to a 4 by 4 matrix. That's crucial in our approach. Why? Because we're talking about parameterizing hypercomplex layers, fully connected layers, convolutional layers, and so on. Because we can basically build the weight matrix, the neural network weight matrix, as a sum of Kronecker products. And this sum of Kronecker products has basically 3 players. The first player is N, that parameterize basically the convolution and the layer. N is an hyperparameter that defines the domain in which the layer or the model operates. So for example, if we set n equal to 2, we can simulate the complex domain. If we set n equal to 4, we can simulate the Quaternion domain, and so on. But most importantly, n can be any real valued number. So we can set also n equal to 3, n equal to 5, and so on. And that's really important because K-Dixon algebras only exist at predefined for predefined values of n. So basically, we have n equal to 2 complex for Quaternion, 8 octonions, but there's nothing in the middle. The second player is the matrix A, or the matrices A, that learns the algebra rules or the filter organization directly from data, and define basically the algebra rules. The last player is the matrix F, or again, matrix F that encloses the convolutional filters, all the weights and or the weights for the fully connected layer. So how this stuff work? Basically, if we set n equal to 4, we said that we can simulate the Quaternion domain. How? In this way. So we have 4 A matrices, so we have A1, A2, A3, and A4 that encode the algebra root. So they tell where the filters F1, F2, F3, F4 have to go in the final weight matrix. You can see that with this with the sum of Kronecker products, basically we can build the matrix W, and if you remember, the matrix W is exactly the same the one for Hamilton product. We can build the Hamilton product by sum of Kronecker products. Most interestingly, since n is an hyperparameter, we can set n to a desired value. And a reduction of parameters in this approach is 1 over n. So if we set n equal to 4, we have a reduction to 1 over 4 parameters like Quaternions. But if we set n equal to 8, we have a reduction of parameters to 1 over 8. And that's incredible. It's almost the 90% of parameters with respect to a real value baseline. And we can go further. So we can set n to any desired value and still preserve a similar hypercomplex decomposition, so hypercomplex properties. So the sharing of parameters, the reduction of parameters, and so on, for any desired value of n. Okay, does this stuff work? And the answer is yes. We tested in lots of problems, both images and audio applications. Starting from images, this is a plot from some tests we conduct on the CIFAR-10 dataset, and basically you have to focus on the reddish models that achieve the best performance, while drastically, crucially reduce the number of parameters for any model we test. So different ResNets, different VGGs, we test up to ResNet 152, so lots of parameters, and it is and the real valued ResNet 152 is the foremost at the right with almost 55 million parameters, and we reduce it to 10 or 20 million parameters. If you want to have a look at the code is publicly available on GitHub. You can also play with some tutorials, with some to example on the notebook. Here, a second example, it is very important, this example, since it is tested on the CIFAR-10 dataset that contains RGB images. We can see that in each run we test with different models. Again, we test here different ResNets. The configuration with n equal to 3 far exceed outperform other configurations. Basically, we can process RGB images in their natural domain by setting n equal to 3 without adding any additional useless information, which basically comes from the additional pumping channel, for example, in Quaternion neural networks. Another test we conduct is, or application which we test our approach is multi-view breast cancer detection. Why? Because usually mammography exams are composed of 4x X-ray images that are highly correlated. And usually a clinician, when has to take a decision among the detection of breast cancer or benign or malignant mass, make use of all the four views. We have a complete views of the exam. And here I report just an example, just a figure, but basically we exploit the hypercomplex properties, algebra properties, and the PHC layer to model these multiple views as a single entity and exploiting correlations among multiple views to have a complete view over the exam. Basically, here we can see that the right breast has a mass. You can see the lighter zone on the right breast that is highlighted in the saliency map and reported also on the activation map. The left breast has no malignant masses, and this is clear also from the saliency map that does not highlight any clear region, but it basically contains some information from the other breast due to the sharing of parameters among the views. We test this approach also on some image synthesizing task, in particular the image-to-image translation task. This task is quite common for generative models since it deals with the translation of an input image from a source domain to a target domain. So basically imagine that we can translate the image of a mountain from winter to summer by preserving the same structure of the mountain and removing the snow and adding, for example, the grass and the sun. This task can be performed in two ways, so learning the target domain from a reference image or learning the style code from a random Latin code. With that, the approach considering the StarGAN V2 as baseline, I want to recall that the StarGAN with V2 is a very huge model, lots of parameters, and that we can reduce such number of parameters by to 1/3 or 1/4. This is crucial because especially generative models are huge models, as you saw also, I don't know, Imagen and Stable Diffusion and something like that, huge models, and our approaches can basically make such huge models more accessible to everyone with a lower budget. And you can see here the image-to-image translation task, in particular the reference analysis. So we learn the reference style from the reference image, and we translate the source image in the new target domain learned from the reference image. We can see that the two rightmost column generate value images with respect to both real value model and Quaternion value model. As well, also in the latent analysis, so the reference here is learned from a randomly sampled latent code, and you can see, for example, images from the real value StarGAN V2 are quite, I like to say, synthetic, while the images from our approach are quite more natural. Also, Quaternion StarGAN sometimes fail to properly translate all the attributes. Again, the code is publicly available, so anyone can repeat the experiments or download the checkpoints and something like that. We can go on. Another application you can see is that when we deal with sound event detection, in particularly as we seen ambisonic signals for 3D audio, which is quite crucial also in application like extended reality, augmented reality, to build an immersive 3D audio scene. We can extract 4 amplitudes coming from the 4 microphones and 4 phases information. What is usually done is that the 4 amplitudes can be encapsulated in a quaternion and then processed with Quaternion neural networks. But with the hypercomplex neural networks and with especially parameterized hypercomplex neural networks, we can encapsulate the complete input, so the 4 phases and the 4 amplitudes, in a single entity, so in a 8-channel input, by easily setting n equal to 8. So at the end, we have more information. We can process more information with less parameters. We test this task on a sound event detection task. We can see that basically the configuration with n equals to 2 outperform the others because we consider a setnet which has just 1.6 million parameters. Imagine that the n equal to 2 configuration has 8K parameters, 800K parameters, but the n equal to 8 has only 200K parameters. So a very, very small network. So we decided to take a setnet which already is a small network. We reduce drastically the number of parameters, but we see that while, for example, the n equal to 4 does not outperform the real valued model, but gain a lot of saving in both training and inference time, and also consequently storage memory for checkpoints. This is an important fact for especially for audio applications, for embedded systems, that we can have a trade-off between models performance and computational requirements and training and inference time. So I want to have the second recap, and do some consideration among such approaches. We have seen that parameterized hypercomplex neural networks can operate in any domain where n is an hyperparameter set by the user, or also tuned by the model, if you want. That, for example, they can process RGB color images by easily setting n equal to 3 and processing them in their natural domain, so without annexing further additional channels, useless channels, and reducing the number of parameters to 1/3. As well, we can process multi-channel signals, for example, multi-channel audio signals with 4, 8 channels, and also 16 channels, for example, easily setting the hyperparameter n, and consequently crucially reducing the number of parameters. So I want to conclude saying that Quaternion and hypercomplex numbers seem just theoretical stuff, some mathematical stuff far away from what we love, from audio, deep learning, and other approaches like that. But indeed, they can be easily and effectively employed in practical applications. For example, we have seen that we can process natural images, biomedical images, multi-channel audio, and we are working also on other stuff. And I know, it works. It works, and it is good to also reduce the computational requirements of the models, especially in this time when there's a research branch that takes a model and pushes to lots of parameters, lots of computational requirements. I think that it is also important to cover a pathway to take and preserve this model accessible to everyone, and not only for big companies or higher budgets. I want to thanks again for inviting me, and thank you for the attention. And these are some references using the talk, and if you're curious, you can look at the code. They're basically in the my repositories, Elegan 23, or ISPAN, which is the repository of the ISPAN lab.